In this lesson we're going to look at Chatellier's principle. Before we discuss that and its uses, let's just remind ourselves what we learned in the last lesson about reversible reactions. We learned that many reactions in chemistry are reversible. That means that they can go in the forward direction or in the reverse direction. So for example, here we have a reversible reaction, and you notice that straight away by this sign here where you've got the two arrows in both directions. And what happens is that A and B react to produce C and D, but C and D will also react again to reproduce A and B. So you've got constantly two reactions going on. You've got a forward reaction and a reverse reaction or back reaction. Now we also learned that when a reversible reaction is taking place in a closed system, there we go, let's represent that with as a closed system, and no matter can enter or leave that closed system, then the reversible reaction will eventually reach a position of dynamic equilibrium. And when it's in dynamic equilibrium, the relative amounts of the reactants and the products stop changing, okay? They become fixed. Now in Le Chatelier's principle, what happens is this, is that if once dynamic equilibrium has been reached in a reversible reaction, if we then change the conditions of the reaction, now by conditions we mean, for example, the temperature at which the reactants are reacting, or the pressure, or for example the concentration of any of the reactants or products, then the reaction will select a direction, either the forward direction or the reverse reaction direction, in order to oppose the changes that are being made. Let's just spell that out for you. So we can say, if the reaction conditions are changed, then the reaction will favour the direction that opposes that change. Another way of saying that is that the position of equilibrium of the reaction will shift so as to oppose that change. So these two statements here really are different ways of stating the same thing. Now, to help us understand this principle, let's have a look at some examples. Supposing that for our reversible reaction we change the temperature. Okay, now before we consider what effect that has, let's just assume that in this particular reaction that the forward reaction is exothermic. That means that as we go in this direction, as C and D is produced, then heat will be released during the reaction. Now that always means that if one direction is exothermic, then always the other direction will be endothermic. That means heat will be absorbed. So going this way to the right, heat is released, exothermic. Going to the left, heat is absorbed, endothermic. Now then, what happens if I increase the temperature? For example, if I heat the vessel in which the reaction is taking place. Okay, what happens if that temperature increases? Now, Le Chatelier's principle states that the reaction will favour the direction which opposes the change made. So if I'm increasing the temperature, then it will favour the direction which results in a reduction of temperature. In other words, it will favour the direction that absorbs heat. And in this case, that is in the reverse direction. So in this particular case, the reverse reaction will be favoured. And as a consequence, the yield of A and B will increase, which means that the yield of C and D reduces. So that's what happens when we get a change in temperature. What about when we have a change in pressure? Now, changes in pressure in reversible reactions only become significant when gases are involved. Okay, so in this particular reaction we've got three gases. We've got A plus B reacting to produce gas C. Now in this type of reaction, what you've got to look at is the number of moles of gas that are involved. Okay, so you've got to look carefully at these numbers here, okay, by the side of the gases, the number of moles. So in this case, say we've got 3 moles of A, 1 mole of B, and that's producing, say, 2 moles of gas C. Now, in order to understand what happens when we change the pressure, first of all, you've got to count the number of moles on either side of the equation. So on this side, we've got 3 moles plus 1 mole. The 1 isn't written there, but there's 1 mole there. Okay, 3 moles plus 1 mole gives us 4 moles of gas. And on this side we've got 2 moles of gas. Now what does that mean in terms of pressure? Where is the pressure greatest? Where is the pressure least? Well, supposing that you took those 4 moles of gas and put them inside a tin can, sealed the tin can, and these 2 moles and put these inside an identical tin can, sealed the tin can, in which tin can would the pressure be greatest? Well, it would be greatest inside this tin can with the 4 moles. Okay, so 4 moles of any ideal gas will produce exactly twice the pressure as 2 moles of any gas. So the gases in this side of the equation result in the greatest pressure, and that is important. So then what happens when we change the pressure? For example, we increase the pressure. So if the pressure is increased, the favoured direction will be the direction that results in a reduction in the number of gas moles. Okay, in this case it will be the forward direction of the reaction, because there are only 2 moles on this side and there are 4 moles on the other. Okay, so the forward direction will be favoured and the yield of gas C will increase. Conversely, if we reduce the pressure, then the backward or reverse reaction will be favoured, because the reaction will adopt the direction that opposes that change and it will try to increase the pressure. Alright, so that's the effect of temperature and pressure on the position of equilibrium, on the direction that a reversible reaction will go. In the next lesson we'll look at the effects of concentration and of catalysts on the position of equilibrium of a reversible reaction.